what is up? This is Radka Kadim, and welcome to this video in physics. So this is about radioactivity. So if you're new to my channel, please make sure that you do subscribe and also like our channel. So for those that have been following, when we talk about radioactivity, we are talking about different types of radiation, or simply let's say radioactive isotopes. Okay, radioactive isotopes. So what you need to understand when it comes to radiation or radioactivity is that there is an important term that you must be able to understand, and this is half-life. Okay, the half-life of an isotope. Okay. Now, what is half-life? So half-life, this is the time it takes for half of the nuclei, okay, nuclei to decay. So half-life, this is the time it takes for half of the nuclei to decay. So what we mean by this is when you talk about this substance, for example, uranium is a radioactive substance. So it is uranium-238 when you check on the periodic table, and 92. So this uranium must be able to disintegrate or form into another maybe element by undergoing the gamma, beta, and also alpha. So if it is undergoing a gamma, an alpha radiation, which is an helium atom, okay, so it can simply form another radioactive substance, okay, and this can be called thorium, which is 234. So what you do is this 238 minus this one, you get 234, and 92 minus 2 is just the 90. Okay. And now what is going to happen is that this can continue and continue. So the mass of this uranium, okay, so let's say maybe you have the mass of uranium at maybe 200 grams. So if it undergoes a decay or disintegrate into another substance, so you find that maybe at some point the mass is going to be 50 grams. So the half-life, which has got the relationship between the activity and also the time. Okay, so when you look at the time, what will happen is that the time will actually continue to increase while this will actually reduce. Okay, so the activity will reduce while the time will increase. Okay, so for example, let's say the half-life the half-life of uranium. So the half-life of uranium 238. 238 is 4.5 times 10 to the power 9 years. Okay. So some of the radioactive material or these isotopes they have, so meaning it would take 4.5 times 10 to the power 9. Okay. This is almost a billion years. Okay. Let's say maybe we can have 45 uh, 45 billion, okay, years for uranium to become another element or for just it to decay. Okay. And then maybe also this another element, radioactive element like thorium. So thorium as a symbol for TH, okay, TH, and it has a mass of 234. Okay, like for example, just this one. Okay, 234. So 234, this one has a half-life of 24.5. So 24.5 days. Okay, so this is just probably like 3 months and so on. Okay, etc. etc. Now you find that it will take millions of years for uranium for uranium piece of uranium to become a lead substance. Okay, so lead, which is on the periodic table, so that symbol Pb. So what you're simply saying is that it will take many years for something to become a stable substance. Okay, so now let us look at the actual example. How to go about finding the half-life, or how to just understand stuff. Okay, so let us look at calculations on half-life. Okay, so example. Okay, so if a certain isotope has a half-life of 2 minutes, okay, so 2 minutes, and has a mass of 12 grams. Okay. Okay, so let us perform some calculation. Okay. So what you have to do is you have to come up with a table. Come up with a simple table, okay? So this table is very helpful. So make sure that we understand what is happening. So the idea is that they'll give you the time as the half-life, okay? And the starting mass is that. So here we put time, and then here we put the mass of this isotope in grams. So what's going to happen is that if we begin with these 12 grams of isotope, then in 2 minutes, half of that. So what they mean is that if it has a half-life of 2 minutes, so meaning half of these 12 grams would have actually decayed into some other lighter substance. So when the time is 2 minutes, okay, so meaning the starting there is 12. So meaning half of this mass is going to decay, okay? So we are going to have 6 grams, okay? So we're going to have 6 grams. Okay, so 6 grams. Now, the time will increase. This is the key concept as the time keeps on increasing. So, this is the initial time. So, the next half-life will occur when the time is 4 minutes, okay? So, meaning this is a second half-life, or rather the half-life. So, this you are going to have 1 over 2 multiplied by another 1 over 2 times the original mass, which is 12, okay? And when you do that, you're just saying that it is 1 over 2 multiplied by 1 over 2, which is just 1 times 1 is 1, then 2 times 2 is 4. And this will be just like, yeah, so 1 over 4. And then this times 12. So you put there over 1, and this is just going to be 1 times 12 is 12, and divided by 4 times 1 is 4. So 4 into 3, 12, is just 3. So meaning you are going to have 3 grams remaining. Okay. Again, from there, what's going to happen now? Again, you're going to do that. Okay. So now we are moving on to the third half life. Okay. So the initial starting time is that time will keep on increasing by this margin of 2. So the third one will be 4 plus 2. So we have 6. So we have 6. And then we are going to have 3 half-lives, okay? So now, ama half ya tatu, yaratupera fyati 1 over 8, okay? Then multiply by 12. So I'm doing now the direct stuff, because on this one you can simply understand this one as like This one I've just done it like 1 over 2 multiplied by 1 over 2 multiplied by 1 over 2. So 1 times 1 times 1 on top, just 1. Then 2 times 2, it's 4. Times 2, it's 8. Then times the original mass. Then you're going to get, use your calculator. So now you're going to get 1.5 grams. So when the time reaches 6, so the activity will reduce by 1.5. Okay. So then you close off this one. Okay. Then when the time is, so to get the fourth time activity, or rather the time period is 6 plus the initial time, is going to be 8. So this is going to be that. So we have now 4 half-lives, okay? So 4 half-lives is just the 1 over 16 multiplied by 12. So this has given us 0.75 grams. Then maybe the last one, okay? The last one, okay? Okay, so what this implies that to get the next time period is, you say 8 plus the original time, the initial time there. So it's gonna be 10. Okay, so this will be 1 out of 32, okay, multiplied by 12. And this will give, so we're gonna actually have 0.375 grams. Okay, so now if you come up with something like this one, then you can now use the graph to plot now the time versus the activity in form of the mass. So okay, so we're going to put this one on a rough graph paper. Okay, graph paper now, kind of just put these values. Okay, so what we're going to do is the time, okay, so the time is on the x-axis, okay, and then this one, the mass or activity, is going to be on the y-axis. Okay, so just before we get them on the graph, so this is how it's gonna actually look like, just on a piece of paper. So what's gonna happen is just going to draw a rough graph, okay. So then here you can just put this 0, and then this one is going to actually be, let's say the time is 2, 4, so you can just say 2, 4, 6, 8. And also the same thing right here is, okay, so on this part we are going to just extend a bit. Okay, so this is that. Then the upper part, the last one is 4. Okay, so then here we can put 2, 4, 6, 8, even 10. Okay, so let's just put 10 there. So now this is time. Now remember the time is in minutes. Okay, then on this part is we have 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, 11, and 12. So on this part is activity. Okay, so the activity, rather the mass. So now if you go back to this table, then we have, so we are going to have 10, 2,6, 4,3, 6, 1.5, 8, 0.75, 10, 0.375. Okay, so in this case we can just round off these other figures. So this one just give us 2, okay, or maybe it's okay, yeah, even if we don't round them off. So first one is 2,6. So 2,6. So 2 is here. Then 6 is somewhere 2,6. So 2,6 is somewhere here. Okay. And then second one is 4,3. 4,3. So 4, the x is there, and 3 is there. So somewhere there. Then followed by 6,1.5. Okay. 6,1.5. So we have 6 is there, 1.5 on the y-axis. Okay. So 1 is there, and then 1.5 is between. So somewhere there. Okay. And then we also have 8,0.75. Okay, so I'll just say 0.8. Okay, so 8,0.8. So this is going to be 8, 0.8. So this is 1, this is 5, 6, 7, 8. Okay, so 8 is there somewhere there. Then the last one is 10,0.3, so 0.4. So I'm just rounding off this, comes to 3, so that will be 0.4. So 10,0.4. Okay. Okay, so 0. So this is 10, and you look on the other side of on your left side of the y-axis, 0. Is it 0. What? 0.4. So 0.4, somewhere there, 0.5 that one, 0.4 this one. So this is 0.4. So what you're going to have now is a nice smooth curve, okay. And of course, the initial one, okay, you always have to plot the starting point, okay. The starting point is 12, okay. Don't forget this one, okay. So what's going to happen now is you just join this. Of course, whatever I'm doing, you do with a pencil. So kind of join, okay. Like this one. Okay. So this is probably how you can get the graph of a radioactive. Okay, so this is a half-life graph. Okay, so sometimes they can ask you from when you are given this kind of the graph, for instance, they can ask you to find the half-life. Maybe the question is already plotted. So what you just need to do is you just say find the half-life from this graph. So all you have to do is half, okay, multiplied by the original mass, which is the starting mass, 12 grams, 12, and then you're going to get 6 grams. Okay, so now you see that on the y-axis there is mass there, and then all you have to do is get your ruler and then identify where there is 6, and then you draw the dotted lines across, okay, across this one. So you say this one until you meet where the graph is. Then once you do that, and then you drop down, okay, you drop down on the x-axis, because we are looking for the half-life. Okay, so then you also use the dotted lines just like that until you meet the x value down there. So now you can see that the number that is there is normally the half-life. So therefore, so the half-life, is 2 minutes. Okay, half-life is 2 minutes. So this is how you can do it from the statement perspective and also from the graphical perspective. Okay, so guys, thank you so much for watching. If you have a question, you have not subscribed to my channel, please do so. Subscribe, share, and like the video. Share as many as you can. So thank you so much for watching. So if you want to learn more, please subscribe. And yeah, so I'll see you in the next video where we'll be able now to solve a question from the past paper. So thank you so much for watching, and I will see you in the next video.